schedule for June. You don't have to be an employee or an associate of Petrolern. If any of you are interested in giving a talk as part of the program, please don't hesitate to reach out to us at info@petrolern.com. Please make sure that you follow us on LinkedIn to receive updated information about the upcoming talks and other good news from Petrolern. Our next seminar is Friday in the afternoon. That's April 20. No, I'm sorry. She says Friday. Let's try that again. The next seminar is on April 21st, which I believe is a Monday, and I'll be speaking on fiber optic sensing technology for oil and gas and carbon storage applications. I'm sure there's applications to geothermal as well. I just don't have geothermal slides in that slide pack. Can I please ask everyone to mute the microphones except for our speaker? And if you have any questions, please save them for the end. If you'd like, you can type them in the chat session to send them to everyone, and our speaker will answer as many questions as possible at the end of the sessions. For people who wanted to be here today, or if you have to leave in the middle for some reason, don't worry, we're recording all these talks, and you'll be able to find them and the other ones that have been given to date at our website, www.petrolern.com. Okay. So it's my pleasure to introduce John McLennan, who since October of 2009 has been an associate professor in the Department of Chemical Engineering at the University of Utah. He's been a senior research scientist at the Energy and Geoscience Institute and also an adjunct professor in the Department of Civil Engineering since January 2008. He holds a PhD in civil engineering from the University of Toronto, awarded in 1980. He has more than 35 years of experience with petroleum service and technology companies. He worked 9 years for Dallas Schlumberger in their Denver, Tulsa, and Houston facilities. And later he was with TerraTech in Salt Lake City, Avantech International in Houston, and ASRC Energy Services in Anchorage. He's worked on projects that have been concerned with subsurface energy recovery, including hydrocarbons and geothermal, in a variety of reservoir settings throughout the world. His presentation title is Frontier Observatory for Research in Geothermal Energy, Milford Site, Utah. John, it's all yours, and thank you so much.
Thank you, Alan. Thanks everyone at Petrolern. I really appreciate the opportunity for doing a P.A.S.S talk and to talk about, as Alan pointed out, the Frontier Observatory for Research in Geothermal Energy. And that's a field laboratory that's located near a town called Milford. About 1,400 people live in Milford. It's in central Utah. And Frontier Observatory for Research in Geothermal Energy is encapsulated in the acronym FORGE. And so let's just talk a little bit about some of the opportunities and challenges. But first, I always like to express sincere appreciation to the Department of Energy for awarding this particular project to the University of Utah. We also have a number of stakeholders in the state of Utah who have really benefited this project. So with that introduction, we're all kind of familiar with geothermal energy in one form or another. Low temperature, we're certainly familiar with direct use of hot water for recreational purposes. Less so, we don't always think of it, but geothermal energy and low temperature water is extensively used for agriculture, for aquaculture, and for industrial processes. As you can see in this particular diagram, we have a greenhouse in southern Utah that grows most of the poinsettias in the United States. It's commonly used for vegetable drying and other processes like that. And if you have a Gucci bag, it may come from an alligator that was raised in a geothermal setting. The really low-hanging fruit immediately in geothermal is kind of surprising, and it's probably low temperature direct use of geothermal through ground source, where heat is extracted and rejected into the ground in combination with heat pump systems. And as you can see from these statistics here, this is growing extremely rapidly. There's at least 1.5 million units worldwide for heating and cooling, residential and commercial and industrial and complexes. And one of the really great examples is in Colorado. Colorado Mesa University has an extensive ground loop where fluid is circulated through a heat exchange system. And in fact, at this university, they have not turned on their boiler in 10 years. And so substantial opportunities for people. And so what I want to mention is that it's not just hot water and electricity. The low and intermediate temperature geothermal water has extensive applications and utilization for people in the geologic or energy spectrum. We, of course, are more familiar with electrification of geothermal energy, and the advantages of this, of course, are that there are low emissions. It's a 24/7 operation so that you can provide base load power and meet peaking demands in off times. It's nominally renewable and it's vast. It's a low-cost resource once your infrastructure, your wells and your plant are established, and it has a relatively low footprint. As you can see in the top photograph, which is a picture of Pacific Corp's 38 megawatt electric Blundell power plant in central Utah, you can see the plant in the foreground maybe occupies 5 acres, whereas a comparative wind farm in the background has a much larger footprint in a sense. So as you can see, I've highlighted 3 geothermal power plants in the state of Utah alone. Those are Pacific Corp's Blundell plant. In the middle, ENIEL, an Italian company, has the Cove Fort plant, and it produces 25 megawatts of electric. And Cirque Energy's thermal plant, also in central Utah, produces about 10 megawatts. So in many places around the world, there are tremendous opportunities for conventional electrification of geothermal energy. Most of these locations for geothermal energy are logically associated with plate boundaries and tectonic environments where, by virtue of plate movement or other tectonic activity, there are sources of heat that are relatively close to the surface that can be accessed by relatively inexpensive drilling. And in fact, these conventional hydrothermal geothermal locations have 3 things in common. They have a heat source. As we can see, we have a geothermal reservoir that's proximal to some sort of natural heating source. They have natural fractures, as shown in the fracture at left from a plant near Reno, Nevada, an operating plant near Reno, Nevada. And they have in situ heated water that can be convected through these natural fracture systems into a wellbore and to the surface to some sort of a power plant. So as we can see with the schematic on the left, we have a convecting situation where heated water is moved through natural fractures, and these natural fractures are intersected by relatively shallow open boreholes, or at least partially open boreholes, which produce through the fractures to the surface. They produce steam or hot water, which is either flashed and drives a turbine, or it's run through some sort of an auxiliary Rankine source binary power plant where there's a secondary heat extraction and conversion to electricity. So what are the characteristics of these conventional geothermal systems? The characteristics are that we have a large in situ volume of heat, and we also have to produce large volumes of heated water. The message here is that compared with a barrel of oil, which can be combusted and created energy, the energy density of a barrel of water is substantially less. So to create the same amount of energy, you need much more water to run through your power conversion operations. And this water in these conventional geothermal plants is transferred by convective heat transfer through natural fractures. These extensive systems of natural fractures are high permeability. And there's a few plants that have multiple wells that can produce on the order of what a nuclear plant would do. That's approximately 800 megawatts. The geysers in particular in California is noteworthy. On average, an average well might produce 6 megawatts of electricity. there are some extremely substantial wells that may produce up to 50 megawatts of electricity. And just to put that into perspective, let's see what you need in terms of your volumes. So at 392 degrees Fahrenheit, 200 C, and sort of the limit for a binary power plant is maybe 150 degrees C, although more and more those limits are pushed lower. A megawatt from the flow rate of 365 gallons per minute will service maybe 750 to 1,000 homes with the demand in the typical demand in the United States. And so 365 gallons a minute is what? That's like 9 barrels a minute. And so it's not too substantial, but it's reasonable. And I really don't know why. I don't know whether your screens are seeing it, but I'm seeing some odd lines on the screen that I have here. So we're getting Zoom bombed or something. But nevertheless, these conventional geothermal systems, what do they need? They need heat, they need fractures, they need water. Now, this is a difficult combination in much of the continental United States. And so how can we take geothermal energy and move that geothermal energy to a move that geothermal energy to a larger geographic part of the United States? Well, heat, fractures, water. Are there parts of the country where we have some of these? Well, yes, indeed. If we look throughout the country, we can see if we drill to 3 kilometers, which is readily possible now using technologies from the oil and gas industry, for example, we can reach temperatures that are at this sort of transitional point of maybe 150 degrees C. And as you can see from the photograph on the right, if I look at the coloring for 150 degrees C, this occupies a much larger geographic portion of the country. So we have the opportunity by deeper drilling to reach temperature. And if we take this further and we give ourselves the challenge that we want to create the other 2 elements. We have heat, but we want to create fractures and we want to circulate fluid through those fractures. Then we can develop what is called an enhanced geothermal system. And this entails drilling an injection well, hydraulically fracturing that injection well, and drilling a production well to intersect those hydraulic fractures so that you have created a heat exchange system where fluid can be pumped down the injection well. It can pass through a series of hydraulic fractures and pick up heat as it passes through those fractures and be produced up the injection well to the surface and subsequently flashed to steam and drive a turbine and generators. Okay, I was just reading the chat that hopefully we can come up with methods to remove those mystery worm tracks, ant tracks on our screen. So we'll go back. So the FORGE program is designed to test out this concept, to develop technologies. And basically what's going to be happening at the FORGE program is an injection well will be drilled. We'll hydraulically fracture 3 stages at the toe of this injection well. We'll monitor the microseismicity and we'll drill a production well into the seismic cloud and do whatever is required to develop an interconnection on those wells. That's the FORGE well. The FORGE program. In a commercial setting, we would fracture more than just the toe of this well. We would fracture all along the length of the well so that you would have an adequate surface area for heat exchange. So in contrast to a petroleum operation where you're looking for pore pressure depletion, this is a situation where you're doing thermal depletion. So recognizing this and the opportunities that are associated with this, the Department of Energy, about 5 years ago, conceived of the FORGE program. And initially, they developed 5 sites where there were paper studies done at those 5 sites. There were a couple in California, one at Fallon, Nevada, one on the Snake River Plateau in Idaho, and one in at the Newberry Volcano in Oregon, and the Utah program in central Utah. In 2016, this was down selected to 2 locations, Fallon, Nevada, and Milford, Utah. Each location drilled a scientific well and established the merits of the individual site for geothermal energy extraction and for a research laboratory. And then ultimately this was awarded to the Milford site, and this is $130 million expended over 5 years. That $130 million involves developing the infrastructure and research money that would go to use the unfractured portions of these wellbores for Department of Energy awards to study hydraulic fracturing, logging, isolation methodologies, etc. So the concepts of forge and the criteria for forge basically are you need temperatures greater than 350 degrees Fahrenheit at depths that are greater than 5,000 feet, but not substantially greater than 5,000 feet, so that the operational expenditures will be minimized. That's definitely a criterion met at the forge site in Utah. These rocks need to be low permeability granite. It needs to be a thermally conductive regime rather than a thermally convective regime that is associated with, convection is associated with conventional geothermal. The number one criteria also, one of the number one criteria is that there needs to be a low risk from induced seismicity. And this site actually meets those criteria. It's been monitored by the University of Utah actually for about 30 years because of potential for earthquakes. And this is a relatively aseismic region that meets the seismic criteria. Low environmental risks, of course, that you need to minimize any sort of environmental risks that would be associated with surface use and competition with agriculture and other ground use. And as I mentioned earlier, with the thermally conductive situation, that there is no connection to a hydrothermal system. And so in fact, the location in central Utah shown here met all of those criteria. And in fact, the state of Utah likes this location because it falls within what they define as Utah's renewable energy corridor, where in the immediate vicinity, there are 3 geothermal fields, there's a large wind farm, there are 2 solar fields, and actually there's a biogas facility because in the immediate vicinity, there are about 500,000 hogs within about 20 miles that are being raised primarily by one of our partners, which is Smithfield Corporation. And the waste from those hogs are used for generating biogas. Immediately around the facility, we, as I mentioned earlier, we have 3 plants. We have Cirque's thermal plant, we have the Blundell plant, which is within 2 kilometers of Forge, and then relatively close by is ENAL's Cove Fort plant. Now, those plants are hydrothermal. It turns out that the specific geologic regime in our location is a conductive thermal environment. And as you can see from the location photograph here, taken, I don't know, maybe 5 or 6 years ago before any activity, there's relatively little environmental disturbance. We, of course, have done NEPA surveys and archaeological surveys. And it turns out from all of the perspectives here, it is a very, very favorable site for this particular operation. No endangered species, no nearby human activity, and the shallow groundwater is non-potable. So since 2017, we've basically drilled 3 wells, 1 vertical scientific well to about 7,500 feet. That was a barefoot completion, and in that completion, the bottom 200 feet were, well, as I said, they were barefoot, and we've carried out a lot of in situ stress measurements in the barefoot section, and also last year we perforated 2 zones of the well and carried out DFIT and actually larger scale injection tests to confirm proof of concept for injectivity into these wells. And so those were the activities in the early years, and now we're proceeding ahead with developing infrastructure and monitoring systems, particularly seismic monitoring systems, not only for hazards, but for microseismic monitoring while we're fracturing so that we have some idea what the morphology of the fractures are. So this is a photograph looking to the west, and it shows the situation, maybe last May, where we have one relatively shallow monitoring well with a geophone and an accelerometer at its base. And this is in alluvium. So the geologic setting is that there's approximately 3,000 feet of alluvium before the granite contact. The alluvium is derived from erosion of the mountains that you can see to the east. And it's shed and deposited here above the granite, the relatively young granite contact. And so one set of sensors in the alluvium. The well here, which is known as well 7832, is drilled into the granite by about 600 feet. And the past year, we monitored activity by having geophones straddling the contact, 1,200 feet of geophones, 12 geophones 100 feet apart, straddling the granite contact. And in this particular well, in the annulus, we had distributed acoustic sensors cemented in the backside. The primary well that we've been working on for the last 2 years is this well that's designated as 5832. It was drilled to a depth of 7,536 feet. We will, as we move forward, we will use this as a monitoring well. The temperature at 7,500 feet in this well is about 200 degrees centigrade. In the future, and in the immediate future, we're just developing drilling plans right now. We will drill the 2 horizontal wells that I've talked about, and I'll show you schematically in a couple of minutes what these wells are like. The first well is designated as 16A 7832, and it is going to be drilled vertically, and then at a 65-degree tangent, it will be drilled just south of east at 65 degrees to the vertical. And as you can see, it bypasses the 7,500-foot deep well, which is the 5832 well. It's relatively proximal to the seismic monitoring well 7832. It's close to the shallow well 6832, and in the very near future, we're drilling a second monitoring well, 5632, which will go to a depth of about 4,500 feet. The directionality of this well is geologically dictated so that the trajectory of the well is perpendicular to the maximum principal stress, consistent with hydraulic fracturing terminology, and not terminology, but experience, where you're drilling so that the fractures will propagate orthogonal to the well. And this is based on geologic mapping and insights over the past 15 or 20 years. It's based in a range extensional setting and also an FMI log, drilling-induced fractures are shown on the Rose diagram in the bottom right. And so we will drill perpendicular to the trends of the maximum principal stress. Now, so sounds pretty straightforward. Well, the problem with this is that people have been trying to do this for 50 years. It started with the Fenton Hill experience in Los Alamos, New Mexico, which was a scientific success. It went on to Rosemont-Aouis in Cornwall, Sault-Soufriette in France, which is actually generating a small amount of power. Experiments done in the Cooper Basin and recent experiments done in Pohang, Korea. And so there are some obvious technical challenges that DOE has identified because of the difficulties that have been encountered over the last 50-odd years, where people have been working on enhanced geothermal systems. The chance and the opportunities, I say more than a chance, the opportunities that we have now are exploiting directional drilling and hydraulic fracturing and isolation technologies that have been adapted from the oil field to do this. So we will drill the first horizontal well, probably starting in about July this year, starting from the west, drilling to the east, orthogonal to the anticipated direction of maximum principal stress. This is a cross-section of what the well will look like. It's drilled down to a depth, and we're drilling at 65 degrees. 65 degrees is a depth where we may still be able to run wireline logs on bogies without having the tubing convey them. We'll see. And that's why the 65-degree depth was selected rather than a even greater inclination from the vertical. A lot of completions discussion on this well, just because of temperatures that are involved and the potential multiplicity of service conditions that this well can see. Originally, it will serve as an injector, but certainly after both wells are in place and they're connected, there is a possibility that the circulation could come from the second well into the first. And so you have to design the expansion and the contraction of the pipe to take that into account. And this is why there will be a liner hanger and cemented liner, 7-inch liner below the hanger, and cemented 7-inch tieback above the liner. So a relatively, it's a standard oil field completion, but adapted to a geothermal environment. So the upcoming activities will be that we will drill and steer 2 highly deviated wells. This photograph at the left was actually taken at one of the largest fracs that was done at the time. It might have been the largest frac for about 20 years, actually. It was Fenton Hill, Los Alamos was fracked at 50 barrels a minute with slick water and calcium carbonate as fluid loss agent, about 6 million gallons pumped in this well. And just to see that we haven't changed too much, just think that this was in 1983, and we're coming back and we're using slick water, we're using lost circulation additives or something that is proppant. I mean, this was 100 mesh calcium carbonate and high rate stimulations. So there's still lessons to learn, but the principle of Forge is that we will drill the first production well. We will create 3 moderate-sized fractures right at the toe of this well, probably using slick water, possibly using lower rate injection in one of the stages, and possibly using a large cool-down pad and a cross-link fluid in one stage. That's yet to be decided. That's down the line. We will monitor the microseismicity of these wells and we'll drill into the cloud. And hopefully we will have intersection with the fractures. If not, there'll have to be remedial work on both wells to create the interconnection. And so you have 2 wells that are interconnected, that you've established this interconnection in the 2 wells. And what that leaves is that leaves the rest of this real estate along the length of this well for the Department of Energy to issue solicitations for people to use these wells as a field laboratory for testing out hydraulic fracturing technologies, testing out monitoring systems, testing out packers and other isolation systems. And so there are a lot of technical challenges that are associated with this type of situation. And the situation is well demonstrated by this Venn diagram that was conceived by Bill Dershowitz from Golder, that these enhanced geothermal systems are an intersection of temperature, an ideal surface area situation, and a low permeability conductive regime. And to get that, you have to face some challenges, and the temperature challenges are high temperature. That high temperature definitely affects your drilling and your completion technologies. Drilling in these granitic wells has historically been extremely low. You feel people have felt happy when they've been drilling 10 feet an hour through these granites, bits lasting 40 hours. And so one of the real challenges with these operations is improving drilling technologies by bits selection, improve motor performance at higher temperatures, and definitely application of technologies such as mechanical specific energy. Logging, same issues, is that conveyance is going to be an issue. Ideally, we can run these wells on bogies or possibly on tractors, but they may have to be tubing conveyed. Through tubing logging is available. And so ultimately also thermal management and making sure that the depletion lasts over the amortized life of these wells, which for geothermal, unlike oil and gas, it's a 30-year amortization period that is required. And so drilling huge challenges. You can see a tricone that was used and the wear on this tricone bit. And what we're really trying to do is introduce concepts from the oil and gas industry that were based on mechanical specific energy, looking at how optimizing the amount of energy that is expended at the bit. So this is going to be a real opportunity in these particular wells. We're also interested in isolation technologies. These high temperatures and relatively high pressures to break down these granitic formations require very, very stout isolation technologies. This is a picture in the upper left of an inflatable packer that failed. That probably failed right about at operational conditions, possibly right near operational conditions. But what we've experienced at the Forge site is we've experienced mechanical packers failing much below operational conditions. So what you can see is packer rubbers in the left-hand photograph. Here is a virgin packer, and here is one that failed much below operating specifications for advertised specifications for the packer. Not only the rubbers, but also the dogs and the slips have failed in these packers. And here's actually a picture of the rubber coming out of the hole. So you have to be able to isolate in these situations, because you have to be able to create multiple hydraulic fractures. And so isolation technology is a big area of research that is prompted by the high temperature environment. The other requirement is that significant reservoir characterization is required, because even though it is a conductive regime, there are a multiplicity of natural fractures that are present. So extensive identification of these natural fractures and modeling these natural fractures, there's significant opportunities for modeling discrete natural fracture networks with sophisticated porothermoelastic considerations. You can ask yourself many geomechanical questions in these. What kind of fracture systems am I created? You know, some of the incipient natural fractures are not preferentially oriented. So are they going to propagate in shear? Are they going to self-propagate? Or do they ultimately become effective edge cracks, as shown here? Very good work done by Gassimi at University of Oklahoma and his students in terms of understanding this. So with the monitoring and the experiments going on in this well, there'll be possibility to identify fracture propagation mechanisms, numerical modeling. This is just an example on the left of an FMI log that was run before hydraulic fracturing, and on the right after hydraulic fracturing. And it's very interesting to see that even in these wells, there were tensile events that were formed on the FMI, 180 degrees apart, axial fractures. And the interesting thing about this is the question is that were these created during the drilling? It's unlikely. Or were they created by thermoelastic effects during cool down because of the drilling? And so certainly in the open hole zone of the one well that we stimulated, there are vertical natural fractures that occurred, and the shear fractures were fundamentally ignored. We've carried out a lot of injection tests on these particular wells, and we've looked at a number of things in terms of trying to understand defect technologies and actually trying to replace defect technologies with some flowback technologies that have been talked about by people from Syntef and certainly by Savitsky and Dudley at Shell have talked about it, where flowback offers the opportunity to do a stress measurement program in a couple of hours as compared to maybe 21, 25 hours that we had to let this shut in for a defect measurement. So this is a situation where we have the opportunity to test out geomechanical concepts, measurement concepts, stimulation concepts, and we're adapting petroleum engineering technology, and we're very, very conscious of what people have learned in the petroleum industry, and particularly lately in terms of designing our completions, where there's a real sense now in the petroleum industry of the difficulties that are occurred with poor cement jobs. And so we're really trying to pay a lot of attention in terms of designing these wells and implementing cementing and completion technology. So I think I've basically talked about this, but bottom line from all of these learnings is that one of the things that we're very, very interested in is developing methods for conformance control. Because you have N fractures along the length of this well, how do you control where the fluids go into these fractures? And so that is a big deal. So geothermal questions, geomechanical questions, you want to know whether you can create discrete conductive fracture networks at multiple locations. That's one of the #1 geomechanical questions. You do not want short circuiting. You do not want substantial interaction between these two fracture systems. Secondly, can these conductive fracture networks propagate independently? And as I mentioned, avoiding substantial interaction between the fracture systems interconnections that minimize the surface area that you encounter. So technical geothermal questions. Always in the back of our mind, though, is induced seismicity and creating seismic events that are undesirable. So safe operations are the #1 primary concern, watching for hazards, seismic hazards. We will use the acoustic active and passive events to comprehend the reservoir and the fracture morphology, but we're conscious of induced seismicity. One of the real examples for this is Basel in 2009, where they weren't extremely large seismic events, but they brought to mind the events that occurred in Basel in 1356, where the entire city was destroyed by, I think it was in excess of a magnitude 6 earthquake. And so in situations where you have the potential for shear motion, you have the potential for seismicity. This energy expended during hydraulic fracturing is always consistent with some level of microseismicity. The challenge is to mitigate this and to find geologic regimes where it is acceptable. The second and final engineering challenge, as I wrap up here, is controlling the flow through these fractures. This may be the greatest challenge that we have. So we can see this schematic flow here showing nicely through a fracture, beautifully intersecting a production well, that you flow fluid through a fracture system. You extract heat convectively, conductively into the flowing fluid. It's produced out the producing well and goes to the surface to produce electricity. But let's take another schematic and let's look at this from the point of view where you have multiple fractures existing in your system. What happens in a system where you're injecting, where there's a multiplicity of fractures? Well, the situation is that dominantly, just strictly on the basis of fluid mechanics and viscous losses that are going to occur in these fractures, is that preferentially the fluid will go through the first fracture that it sees. And unfortunately, in geothermal situations, it's catalytic, because as I flow through fluid through that fracture system, at least part of that fracture system will be cooled. And as that fracture system is cooled, thermoelastic coupling causes an increase in aperture of that system, and preferentially more and more fluid will flow through. So one of the real challenges is mechanical control of fracture systems or chemical control through diversion of one form or another. And so to conclude, this is a tremendous opportunity for the geothermal community, for the geomechanical community, for the oil and gas community to look at exploration technologies, characterizing reservoirs, reducing drilling costs, and all sorts of things that are indicated on this list. So fantastic opportunity that the DOE has envisioned and put into place. And so at this point, I'd be happy to try and address any questions that might have come up during the talk or you've conceived of afterwards. Thank you.
Thank you very much. This is Alan. Can you hear me?
Yes.
That was an outstanding presentation. We have a number of questions here. Since I'm the moderator, I'm going to stick mine in first. Hey, I'm not an expert in this area. Besides using the Silixa distributed acoustic sensing fiber, which is, I think, a great idea, you're getting to temperatures here over 200 degrees C. Are the geophones getting close to their temperature limit?
Well, you know, I'm not a specialist in this area. and maybe there's somebody who's tuned in that is, but when we run them in the future, we'll keep them below 150 degrees C for medium-term installations. And so what that'll mean is in the vertical deep observation well that we have, we've fractured up to about 6,500 feet in that well. We'll install a bridge plug above that depth, and when we run geophones in that well, we'll keep them below 150 degrees C. So indeed, you're right. I believe that there are some technologies that can handle that temperature, higher temperatures for a shorter period of time, but I would have to defer to my colleagues on that particular situation.
Yeah, you can get up to about 200, and then you don't have that limitation to an extent with the fiber. Some of the other questions that have come in from the audience. Here's one. Have you looked at flow control devices applications for flow conformance?
Yeah, we've looked at even things like sliding sleeves. To start with, we've looked at things like sliding sleeves. The situation in this well, though, is that it's 7-inch casing, and the 7-inch casing is run to be consistent with the geothermal requirements that no matter what, you need a large amount of water that's coming through this device. We've talked to the sliding sleeve companies, and there are tools that we're aware of that go to 5.5-inch casing, and these companies are interested, looking for bigger casing. But there are mechanical devices that could be conceived. The first chore on this is we want to make sure that we can interconnect the two wells with the hydraulic fractures. The second chore, as the individual has pointed out, is that mechanical control is going, or some form of control is going to be absolutely essential for this to be commercially successful. So right now, our primary task is to look at interconnection. This is a research opportunity for looking at devices, mechanical or chemical, for controlling flow at some time in the future.
Thank you. Here's another question from another participant. How would you score the use of CBL or VDL logs to quantify the cement job?
The logs that we've run in the past have been we've run both CBL and then some of the pulse type technologies. In particular, we've used Schlumberger's isolation scanner. I'm very fond of the isolation scanner. In fact, in one of the holes that we drilled, the deeper hole, we used a foam cement job, and the isolation scanner naturally was much improved for over the standard CBL. But the background to the question is that it is absolutely essential to carry out an appropriate and confirmed cement job in these wells. And so I think that the expenditures need to go to cement design, and as the individual has pointed out, to sophisticated logging that is carried out in these logs. And I think it's going to take more than just a conventional CBL log. Even with the multi-sensor devices and the pulse technologies, you really cannot skimp on cement design.
Okay, here's sort of a combination question. Person is asking why you've chosen to do this for the horizontal injector toe down as opposed to toe up. That's question number one.
Okay, so I think we're less worried about pumping the injector than we are producing out of the injector, and so we'll have compression pumping down the injector rather than being worried about the injector being drained. That's one aspect. The second aspect is that this is sort of new territory. It is one of the first highly inclined wells in the geothermal sphere, in rock that drills very slowly, and so we just want to take it one step at a time and deal with a relatively conventional type system. And indeed, at one time we wanted to go to 90, but we were convinced by our advisory group that they wanted us to back off to an inclination to 65. So
Okay.
maybe I'm missing something, but I think the situation is here that there's less worry about producing out of this well and pumps than there is in a conventional oil field situation.
So a follow-up question, I don't quite understand. I'll read this question. Is the drilling going to be done using traditional overbalanced drilling fluid, or would you consider some sort of managed pressure or under pressure drilling?
So that's a fantastic question. This rock, although it drills slowly, it's basically a hydrostatic pressure environment, and the porosity is so low that really talking about hydrostatic pressure is almost a misnomer. We will start off in this well using conventional technology. We're trying to push PDC bits into the geothermal business, and we'll be drilling very, very slightly above balance under most cases. Now, that being said, there is a real future for underbalanced technologies and hammer drilling and percussion drilling and air operated drilling in the geothermal business. And this was dramatically shown by the deep well in Finland that had very, very good success with underbalanced drilling. So another excellent question. We're going to be relatively conservative at this particular time. We're conceiving and considering air drilling some of the vertical monitoring wells that we're planning in the future, so that we can get some level of experience before we try it on one of the deeper wells.
One more question. And when I'm reading this, there's one after that too. I assume the WL stands for wireline, but in any event, I heard you ran a WL operation on a previous well. What can you tell me about the quality of the logs acquired, and what are the lessons learned from the previous well that you drilled?
Well, let me just go back to this FMI. One, and if I can find it, we had very good success, surprisingly good success, not surprisingly, but we had extremely good success with the logging operations. Now, in fact, we were lucky in this well that, the static bottom hole temperature of the well was 200 degrees C. But when you drill these wells, you're running mud chillers. We continuously ran mud chillers. And so the bottom hole temperature when we actually ran the logging was about 175 degrees C. This is an FMI. The Sandia National Labs has an acoustic imager that's been used at very high temperatures in vertical wells. We're looking at potentially putting centralizers on that and actually using it in this inclined well. We've had very good success with the wells because we've had adequate cool down. Now, in one recent campaign, we fractured the toe of the well and we ran an FMI. By the time we finished the FMI, the temperature was high enough that we decided that we couldn't run a UBI, which was unfortunate. So temperature is a real issue. We're really looking forward to the logging operations in these deeper, hotter wells, because they'll be even hotter. The static temperature at the toe is about 235 degrees C. So we had good luck with the FMI. I suspect you'll have good luck with the acoustic tools. We ran a DSI that worked extremely well, but the temperature was cool enough. One of the problems that we encounter is that our level of experience in interpreting triple combo data in a geothermal and a granitic setting is maybe less, at least from my perspective, is maybe less than what it is in a sedimentary sequence. And so we had great luck with the wells. Where the real challenges are going to be are on these deep inclined wells, where we may be doing through tubing logging, where we'll run in the hole with a device that has a bit at the end with a hole in it that will deploy FMI actually I think a DSI can go through that as well and come back up the hole on tubing. The advantage being that through that device we can circulate. Although the cheaper opportunity is if we can run these logs on bogies, which are basically wheeled type devices that will allow us to go down, and the vendors feel comfortable that maybe 65 degrees will work, and maybe the temperatures are adequate with circulation to be able to use even mechanically powered devices. So we've had good luck with logging to date.
That's great. There's another question. I'm trying to sort of figure this out, what the person is actually asking, but it's about permeability. So let's build on that.
Okay.
What's the magnitude of the permeability? Why is it that magnitude? Is the permeability anisotropic, and so on?
Laboratory evaluations of permeability have shown low microdarcy range on these granites, which actually surprised me. I thought they'd be lower than that, but I feel pretty comfortable with the measurements. In the field, we've determined permeability from DFIT type tests, and the permeability with the DFIT is in that same order of magnitude, low microdarcy, maybe 30, 40, 50 microdarcy. And of course, the DFIT type permeabilities are going to be some reflection of natural fracture and low matrix permeability. As to anisotropy, we have to presume that the anisotropy is going to correlate with the natural fracture direction. We have three dominant fracture directions: a preferential direction of fractures that are just east of north, and then one system that is less developed but is east-west. And so based on that, we think that I would speculate that the natural fracture anisotropy is going to be relatively small because we have two essentially orthogonal fracture systems.
Okay.
But another good question. I mean, that's an important question here.
John, I think something that the question might mean is that why the perm should be low, should be very low. Is there any reason? Is it a requirement for geothermal systems?
Well, characteristically, you're talking about igneous systems that without fractures, the permeability will be naturally low. The porosity in this is less than maybe 1%. And so you have low matrix permeability. You do not want to have an extensively fractured system because that would give you the opportunity to make it a convective fracture system. So you want something that's conductive, where the heat, the thermal gradient through this reservoir indicates that heat is moved through this reservoir by virtue of conduction. So a convection thermal gradient shows a relatively constant temperature with depth. A conductive thermal gradient shows a gradient that's like that mirrors maybe a hydrostatic gradient, where the temperature decreases gradually as depth decreases. And so the permeability needs to be low so that it can be fundamentally a conductive environment where actual stimulation is required to create the an effective natural fracture system. I don't know whether that answered the question.
Yes, I think no, I'm looking at the follow-ups. Oops, yes, why, sorry, thank you. Okay. Hey, are you writing your own modeling program to model systems like this? And before I give you a chance to answer, hi, I no longer work for the DOE, so I don't have to be impartial to the national labs, but both Livermore, Berkeley, and Los Alamos have some pretty darn good modeling software for geomechanics, for flow. And in the case of Livermore, a lot of this was developed for nuclear application, shockwave propagation, and so on. So I'm sure they've looked at it in all types of rocks and not just sedimentary. Are you writing your own software, and/or have you considered reaching out to those labs for advice?
Yeah, we have a fairly extensive modeling effort that goes on, but in addition to that, some of the R&D opportunities in the future involve modeling where I'm certain the national labs will exercise their own capabilities. Our modeling effort is a team formed by the modelers at INL using their Falcon platform. We also,
that's good too. Yeah.
We also collaborate extensively with Golder. And where Golder shines is that in terms of developing the discrete fracture networks that are appropriate. And then our other partner in this is Itasca Corporation, where Itasca is going to use their Excite is using their Excite platform for discrete fracture modeling. And so it's a combination of we're doing a set of modeling on our own so that we can conceive what the fracture geometries are going to look like at the toe of this fracture, so that we can plan the stimulations that we'll do in advance of drilling the second well. And then there will be research opportunities down the road for people to explore using their own codes.
Hey, John, I want to thank you very much on behalf of Petrolern and on behalf of the audience. That was an outstanding presentation. I'm sorry there were these suspect fractures propagating through your slides. But,
well, I hadn't thought of that. That's very appropriate.
Well, at one point, I shouldn't say, but Hamid said, maybe John is generating his own thermal fracture.
No, I plead ignorance on this one. But yeah, I'd like to thank everyone for the opportunity, and please, if there are any further questions or recommendations, I would really like to hear from anybody in the audience. And if you can't get me directly, you can interact through Petrolern.
So thanks very much again. That was talk number 3 in the series. Talk number 4 is early afternoon on Monday the 21st. It happens to be a talk that I'll be giving, and it's on fiber optic sensing technology for oil and gas and carbon storage applications, but we've already seen a distributed acoustic sensing application here for geothermal. So thank you.